Another growth rate we're going to talk about is the logarithmic growth, which we show with the big O of log n. Here's the logarithmic curve. Now, compare this with the linear curve. As you can see, the linear curve grows at the same rate, but the logarithmic curve slows down at some point. So an algorithm that runs in logarithmic time is more efficient and more scalable than an algorithm that runs in linear or quadratic time. Let's see a real example of this. Let's say we have an array of sorted numbers from 1 to 10, and we want to find the number 10. One way to find the 10 is to iterate over this array using a for loop, going forward until we find the 10. This is called the linear search because it runs in linear time. In the worst case scenario, if the number we're looking for is at the end of our array, we have to inspect every cell in this array to find the target number. The more items we have, the longer this operation is going to take. So the runtime of this algorithm increases linearly and in direct proportion with the size of our array, right? Now, we have another searching algorithm called binary search, and this algorithm runs in logarithmic time. It's much faster than the linear search. Assuming that our array is sorted, we start off by looking at the middle item. Is this item smaller or greater than the value we're looking for? It's smaller, so our target number, in this case 10, must be in the right partition of this array, right? So we don't need to inspect any of the items in the left partition. And with this, we can narrow down our search by half. Now, in the right partition, again, we look at the middle item. Is it smaller or greater than the target value? It's smaller, so again, we ignore the items on the left and focus on the items on the right. So in every step, we're essentially narrowing down our search by half. With this algorithm, if we have 1 million items in our array, we can find the target item with a maximum of 19 comparisons. We don't have to inspect every item in our array. This is logarithmic time in action. We have logarithmic growth in algorithms where we reduce our work by half in every step. You're going to see this a lot in the second part of this series, where we talk about trees and graphs. Unfortunately, I cannot show you an example of this in code now because it's a bit too complex. There are a few things we have to talk about before you're ready to see that in code. But trust me, you'll see that in the code in the future and it will become super easy. For now, all I want you to take away is that an algorithm with logarithmic time is more scalable than one with linear time.